Okay, strap in everyone, because today we are tackling some seriously big
Big
questions.
questions, huh?
The universe, its origins, what it's all about, and maybe even how it all ends. We've got a mountain of stuff to go through from all of you.
Yeah, articles, research papers, someone even sent their own personal notes.
Looks like we've got some deep thinkers out there.
For sure. And they didn't hold back. I mean, we've got everything here.
We're talking parallel universes, the chance we're all living in some kind of, simulation,
There's even some theories about white holes.
like the opposite of black holes.
Exactly. It's a wild mix.
That's what I love. But here's the thing, and this is what makes it so fascinating. These aren't just like sci-fi daydreams. This stuff is rooted in real science.
Oh, absolutely. You know, it really makes you think about that line between hard science and what we call science fiction. It gets blurry.
Totally. Especially when you're dealing with ideas that push the limits of what we even know.
Right. Like, what is even possible?
Okay, let's dive in. First up, an idea that's been around forever, going all the way back to the ancient Greeks, the multiverse theory.
Multiverse, huh?
I'm talking parallel universes, alternate realities. I mean, come on, who hasn't thought about that?
It's a classic.
Yeah.
And such a captivating idea. The basic concept is that, well, our universe, it might not be the only one. Instead, just one of countless others,
All existing at the same time.
maybe even bumping into each other in ways we can't even fathom.
You mentioned different levels of multiverses in your notes. I was reading about the physicist Max Tegmark, his 4 levels of multiverses.
Right.
Even the laws of physics, like they could be different in these other universes.
Oh, yeah. And then there's Brian Greene's work, too. It gets pretty complex.
Well, I don't know.
So, okay, Kegmark's level 1, for example, that's the idea of, an infinite universe, way beyond what we can see, right?
Mhm.
And in different patches of this mega universe, everything could have started a little bit different. Different laws, different stuff happening. It's mind-blowing to think everything that could have happened maybe did happen somewhere out there.
Wow. Okay, so maybe there's a universe where I actually finished writing that book I started, or like one where I'm I don't know, a world-famous astrophysicist.
Hey, why not?
But here's my question. Can we even test this?
Mm.
Is the multiverse even a real scientific theory? Some folks are skeptical.
Oh, huge debate. Some folks say it's more philosophy than science because how can we ever observe it?
Right.
Others think we might find clues, like tiny variations in the cosmic microwave background radiation. Maybe that's a hint other universes are out there, somehow.
So for now, it's still a mystery. Maybe someday we'll have the tech to peek into these other universes, but until then, pure imagination.
Speaking of pushing the boundaries of what's real, let's move on to something that's getting a lot of buzz these days, even in the tech world. Simulation theory.
Whoa. This is the one that really makes you question everything. Okay, be honest. Have you ever felt like, I don't know, reality is just a little bit off?
Like glitching.
Yeah, like something's not quite right.
I know exactly what you mean. And simulation theory says, maybe that feeling isn't so crazy after all. What if our reality is just a super advanced computer program?
A program made by someone way smarter than us.
Right, like way, way smarter.
It's straight out of the Matrix, right?
Totally. Remember those notes I sent about Nick Bostrom, that philosopher?
Yeah, he was talking about super civilizations creating these simulations.
His argument is pretty convincing. And it's not just philosophers thinking about this.
Oh, yeah.
Elon Musk, the tech guy. He said he thinks the odds are good that we're in a simulation.
Whoa. Okay, if we are in a simulation, who made it and why? And wouldn't there be, like, glitches, signs that things aren't what they seem?
Those are the big questions, right? And if it's a really good simulation, maybe we can never tell.
That's a little creepy to think about.
It is, but it makes you think about what reality even is.
Okay, multiverses and simulations.
Yeah.
2 for 2 on the mind-blowing scale. What's next?
All right, prepare for a twist. Remember those notes about black holes?
The cosmic vacuum cleaners.
Yeah, they suck up anything that gets too close. Well, let's flip the script and talk about white hole theory.
Okay, black holes are pretty scary, so they're opposites. Maybe that's something a bit more hopeful. Do they, like, spit things out?
You got it. Imagine a black hole, but instead of pulling things in, it's pushing them out.
Like a black hole in reverse.
Exactly.
Yeah.
Nothing can get in, but things can come out. It's wild.
Whoa. So are we talking about, like, a cosmic fountain? Could they be linked to black holes? Or maybe they're portals to other parts of the universe? Or even, I don't know, other times?
Those are the questions physicists are trying to answer. Some think they could be the other end of a wormhole, a tunnel through space-time.
Right.
But right now, white holes are still mostly theory. We need more research, more observations to figure out what they really are.
If they even exist.
Exactly.
Okay, let's take a deep breath here and jump into something that's about, well, the very fabric of reality. Superfluid spacetime theory. This one's a bit of a head-scratcher, even for me.
Get ready for a wild ride. Have you ever heard of superfluids?
Not really.
So imagine a fluid that flows without any resistance at all.
Like zero friction.
Exactly. Picture a perfectly smooth ice rink. If you slide across it, you just glide forever. That's what a superfluid is like.
Okay, I can picture that. But what does that have to do with space-time?
Well, the idea behind superfluid space-time theory is, what if space-time itself, like the very fabric of the universe, behaves like a superfluid?
Wait, so space itself would be like a fluid?
That's the theory. And this could explain some of the universe's biggest mysteries, like how galaxies formed, why they're shaped the way they are, all that.
Wow, so we're not just talking about the stuff in space, we're talking about space itself acting like a fluid. That changes everything.
Right. It suggests the universe might be way more dynamic and connected than we ever imagined.
All right, brain officially overloaded. And now we come to a theory that challenges the granddaddy of cosmic explanations, the Big Bang. Let's talk about the ekpyrotic universe theory, a universe reborn from fire. That's what we're dealing with now.
Ekpyrotic, it's Greek. It means like a huge fire, a conflagration. And the theory says the universe didn't start with just one big bang, but it's part of this like ongoing cycle of collisions between brains.
Okay, hold on. Brains. I'm going to need a bit more on that.
Fair enough. Imagine our universe as like a flat sheet, a brain, floating in this higher dimensional space.
Higher dimensions.
Yep. And there could be other brains out there that we can't see, also floating around. When these brains smash into each other, boom, massive burst of energy.
And that's what we see as the Big Bang.
Exactly. So the Big Bang wasn't a one-time thing, but just one bounce in this endless cycle of like expansion and contraction.
So the universe is constantly being reborn, no beginning, no end.
That's the idea. And it explains why the universe looks so uniform, so smooth, even over huge distances. But like all theories, it's got its own challenges.
Like what?
Explaining where these brains come from, what makes them collide, all that.
Yeah.
Still a lot to figure out.
Okay, we've covered some seriously wild alternatives, but we can't ignore the one that's still the leading explanation, the Big Bang Theory. It's been the top dog for a reason, right?
Right, and it's important to understand what it actually explains. It doesn't tell us what caused the Big Bang, but it does a great job describing what happened afterwards.
So take us back to the beginning, well, the beginning as we know it. What does the Big Bang tell us about that first moment?
Okay, picture this. It all starts with this unbelievably hot, dense little point, smaller than an atom. Then boom, rapid expansion, cooling down as it grows like crazy.
It's mind-boggling to think about the energy involved.
Totally. And as the universe cools, the first fundamental particles start to form, the building blocks of everything.
So we're going from pure energy to matter.
Exactly. And then gravity comes in, pulls those particles together over millions of years, forming the first stars and galaxies.
So the Big Bang sets the stage for everything we see today. Stars, galaxies, planets, even us.
It's like a cosmic chain reaction.
Yeah.
And there's lots of evidence to back it up. Remember that cosmic microwave background radiation we talked about? It's like a baby picture of the universe showing us what it looked like way back when.
Right. And it's super uniform, just like the Big Bang predicts, which suggests that the universe really did come from a single point. What other evidence supports the Big Bang?
Well, we can see the universe expanding, just like Edwin Hubble discovered. And by measuring the rate of that expansion, we can figure out how old the universe is, which matches up pretty well with what the Big Bang model says.
Okay, so lots of evidence points to the Big Bang. But what about those alternatives? We talked about the steady state theory earlier, the one where the universe is eternal and unchanging. Why did that theory fade away?
As beautiful as the steady state theory was, it just couldn't explain certain things we observed, like those quasars, super bright, distant objects. They didn't fit with the idea of a universe that's always been the same.
Yeah.
And then there's that cosmic microwave background radiation again. The steady state just couldn't account for it.
Right, those echoes of the early universe.
Exactly. But even though it's been mostly rejected, the steady state theory was important. It sparked debates, pushed scientists to find new ways to test their ideas. And that's how science works. You challenge ideas, refine them, and get closer to the truth.
So even wrong ideas can move science forward.
Totally. Okay, let's go back to that mind-blowing multiverse. I'm still wrapping my head around the idea that our universe might be just one of many.
Yeah.
What are some of the different types of multiverses that physicists have come up with. Oh, it gets pretty wild. Physicist Max Tegmark came up with a system where he has 4 levels of multiverses.
4 levels.
Yeah. Level 1 is like, imagine the universe just keeps going and going, way beyond what we can see.
Like forever.
Exactly. And in different parts of this giant universe, things could start it a bit differently, leading to variations in the laws of physics.
So there could be a universe where gravity is a bit stronger, or one where, I don't know, electrons have a different charge.
Right. And it gets even weirder. Tegmark's level 2 says the laws of physics themselves could be different in different universes, like a universe with 5 fundamental forces instead of 4, or where the speed of light is totally different.
Whoa. Okay, that's hard to imagine. What about the other levels?
Okay, level 3 is based on quantum mechanics. It's called the many worlds interpretation. Basically, every time a quantum measurement happens or every time you make a choice, the universe splits.
So, like, every time I decide between coffee or tea, a new universe pops up for each choice.
Exactly. One universe where you had coffee, one where you had tea. Gets a little crazy, I know.
A little. And what about level 4?
All right, this is where it gets really deep. Level 4 says the universe is fundamentally mathematical. Like, every possible math equation, every structure corresponds to a real universe. It's like math is reality.
Whoa, okay, that's deep. But how can we know if any of this is actually true? Can we prove or disprove the multiverse?
That's the million-dollar question. So far, it's just theory. There's no direct evidence.
So it's a playground for theorists for now. But even if we can't see these other universes, are there any hints they might be out there, like indirect clues?
Maybe. Some physicists think collisions between universes could leave marks on the cosmic microwave background radiation.
Oh, really?
Yeah, like faint patterns or strange temperature variations. Others think gravitational waves, those ripples in space-time, could carry information about other universes.
So the search continues. It's pretty exciting to think that we might find proof that our universe isn't alone. But for now, we can at least enjoy the mystery of it all.
For sure. Now, let's bring things back down to Earth, literally. We've been talking about the whole universe, but what about other worlds out there? Planets that could have life. You sent in some stuff about Goldilocks planets.
Yes, the idea of finding a planet that's just right for life, like Goldilocks and the porridge, is fascinating. What makes a planet habitable, and what are the chances we'll find life out there?
All right, for a planet to be habitable, at least for life as we know it, a few things need to be just right.
Like,
first, it needs to be in the habitable zone of its star. That sweet spot where the temperature is right for liquid water on the surface.
Right. Not too hot, not too cold. We've talked about that. But isn't there more to it than just temperature?
Oh, yeah. The planet's size and mass matter a lot, too. If it's too small, it can't hold on to an atmosphere. Too big, and it might become a gas giant, like Jupiter, which isn't good for life as we know it.
So size matters.
Big time. And then there's the planet's composition. What it's made of is key. You need the right elements, like carbon, hydrogen, oxygen, nitrogen. Those are the building blocks of life. And water, of course, on the surface or maybe in underground oceans.
So it's this delicate balance. But with billions of planets in our galaxy alone, it seems like the odds are good that we'll find at least some habitable worlds, right?
Right. And thanks to missions like the Kepler Space Telescope, we now know that planets are incredibly common. Kepler's found thousands of exoplanets, planets around other stars. So out of all those billions, there are bound to be some that are just right for life.
So the search for life beyond Earth isn't just a dream. It's a real scientific quest. It's incredible to think we might be on the verge of discovering life on another planet, maybe even intelligent life.
The implications of that would be huge. It would change everything about how we see ourselves and our place in the universe.
Totally. Even finding microbes on another planet, that would be a huge deal. It would show that life isn't just a fluke here on Earth, but something that could happen all over the universe.
Right. Life could be everywhere.
Okay, let's dive back into the subatomic world for a minute. We've talked about neutrinos, those tiny particles that barely interact with anything, but you mentioned something about a special kind of neutrino, a sterile neutrino. What makes them different, and how do they connect to the mystery of dark matter?
All right, so sterile neutrinos, they're like neutrinos on stealth mode.
Stealth mode.
Yeah. They wouldn't interact with the weak force, one of the 4 fundamental forces of nature.
So they'd be even harder to detect than regular neutrinos.
Way harder. Like ghosts passing through everything.
Yeah.
And that's why they might explain dark matter.
Okay, remind me what dark matter is again.
It's this invisible stuff that makes up most of the mass in the universe. We can't see it, but we know it's there because of its gravity.
Right, so how do these sterile neutrinos fit in?
Because they're so weakly interacting, They wouldn't emit or absorb light. They'd be invisible, but they'd still have mass, which means they'd have gravity.
So they could be the missing mass, the dark matter.
Exactly. If we could prove they exist, it would be a massive discovery.
But if they're so hard to detect, how do we even look for them?
It's tough. One way is to look for weird things happening with other particles, like what they saw in the Mini-Boon experiment at Fermilab.
That was in your notes, right?
Yep. Mini-Boon was studying neutrino oscillations, how neutrinos change from one type to another as they travel, and they found more electron neutrinos than they expected.
Which could be a sign of sterile neutrinos messing things up. So we're trying to catch these neutrinos in the act, see their fingerprints on other particles. It's amazing how scientists piece together these tiny clues.
It really is. And this is just one example. Who knows what other breakthroughs are out there?
Okay, from the smallest particles to the biggest ideas, we've covered a lot. But there's one more we have to talk about. It's captured the imaginations of writers and philosophers for centuries. The simulation hypothesis.
Ah, yes, the simulation hypothesis. Are we all just living in a computer program? It's an idea that's been getting more attention lately, even from some serious scientists.
Why is that?
Well, one reason is just how complex and fine-tuned the universe is. The laws of physics seem perfectly set up for life to exist. Some people think maybe that's a sign that it's all been designed, like a simulation.
Like finding a watch on the beach. It's so intricate, it makes you think someone must have made it.
Right. And for the universe, maybe the watchmaker is some super advanced civilization with crazy computing power.
Okay, but how could we ever know for sure? What would we look for?
That's the tough part. Some say there might be glitches in the simulation, like weird things happening with physics, or unexpected patterns in how matter and energy are spread out.
So we'd be looking for cracks in the matrix.
Exactly. But others say, if it's a really good simulation, we'd never be able to tell. Our fake reality would feel completely real.
So it might be a question we can never answer. Maybe we're in a simulation and we'll never know. It's a cool thought, but kind of creepy too.
I agree. But even if we can't prove it one way or another, it makes you think, doesn't it? About reality, consciousness, and the limits of what we can perceive.
Okay, my brain needs a break after all that. From multiverses to sterile neutrinos to simulated realities, what's the one thing you'd want our listeners to take away from all of this?
I think the most important thing to remember is that science is all about exploration, about always learning. We're constantly making new discoveries, and sometimes those discoveries completely change how we see the universe. That's what makes it so exciting.
It's like we're on this never-ending quest to figure out where we fit in the cosmos, and there's always more to learn.
Exactly. And who knows what incredible things we'll find next. We've been exploring some pretty wild alternatives to the Big Bang Theory, but I think it's time we dive into the reigning champion of cosmic explanations. The Big Bang Theory itself has been the dominant model for a reason, wouldn't you say?
Absolutely. There's mountains of evidence pointing to the Big Bang, but I'm curious, what exactly does it explain? How does it all fit together?
So it's important to remember that the Big Bang Theory doesn't explain everything. It doesn't explain what caused that initial expansion or what, if anything, might have come before it.
Right.
But what it does explain is the evolution of the universe from that incredibly hot, dense state.
Okay.
And it does that remarkably well.
So rewind the cosmic clock about 13.8 billion years. What does the Big Bang tell us about that first moment? What happened afterwards?
Okay, imagine this. The universe starts as this incredibly hot, dense little point, smaller than you can imagine. And then in a fraction of a second, it undergoes this unimaginable expansion, cooling as it rapidly grows.
It's mind-boggling to think about just how much energy must have been involved.
Right. And as the universe cools down, things start to happen. The first fundamental particles start to form. The building blocks of matter, like quarks and leptons, all that good stuff.
So we're going from a universe filled with pure energy to a universe where matter can actually start to take shape.
Exactly, and that's where gravity comes into play. Over millions of years, those clouds of hydrogen and helium drawn together by gravity start to clump together, forming the first stars and galaxies.
So the Big Bang essentially sets the stage for everything we see in the universe today. The stars, the galaxies, the planets, even us. It's like this chain reaction of cosmic creation.
It really is. And we have some pretty convincing evidence for this whole chain of events. Remember that cosmic microwave background radiation?
Yeah.
That's essentially like a baby picture of the universe.
Yeah.
It shows us what the universe looked like just a few 100,000 years after the Big Bang.
Right, and it's incredibly uniform, just as the Big Bang predicts, which suggests the universe did originate from a single point. What other evidence is there for the Big Bang?
Well, we can actually observe the universe expanding, just like Edwin Hubble discovered back in the 1920s. And by measuring the rate of that expansion, we can calculate the age of the universe, which lines up incredibly well with the age predicted by the Big Bang model.
Okay, so we've got multiple lines of evidence pointing to the Big Bang. But I want to circle back to those alternative theories we talked about, like the steady state theory, the one where the universe is eternal and unchanging. Why did that one fall out of favor?
Well, as elegant as the steady state theory was,
Hmm?
it simply couldn't account for some key observations. The discovery of quasars, for example, those incredibly luminous and distant objects.
Right.
They challenged the idea of a universe that's always looked the same. And then, of course, there's the cosmic microwave background radiation again. That just doesn't fit into the steady-state model at all. A steady-state universe wouldn't have that kind of background radiation.
Right. The steady state just couldn't explain those echoes of the early universe. But even though it's been largely discredited, it still played a role in the development of cosmology, wouldn't you say?
Oh, absolutely. It forced scientists to really scrutinize the evidence, to come up with new ways of testing your theories, and that's how science progresses.
Through those challenges and debates.
Exactly. You challenge the existing ideas, you refine them, and hopefully you get closer to the truth.
So even wrong ideas can actually push science forward.
Totally. Okay, so let's go back to that mind-blowing multiverse. I'm still trying to wrap my head around the idea that our universe might be just one of many.
Yeah.
Can you remind me about the different levels of multiverses that physicists have proposed?
Sure. So physicist Max Tegmark proposed this classification system with 4 different levels of multiverses. The first level, level 1, is what we might call a quilted multiverse. The idea is that the universe just extends infinitely beyond our observable horizon.
So it just keeps going and going.
Exactly. And in different regions of this infinite universe, things could have started a little differently.
Okay.
So different initial conditions leading to variations in, say, the laws of physics and the formation of stars and galaxies.
So you're saying there could be a universe out there where gravity is a bit stronger, or one where, I don't know, electrons have a different charge. It's kind of hard to imagine.
It is, and it gets even more out there. Tegmark's Level 2 multiverse proposes that the laws of physics themselves could vary from universe to universe. So imagine a universe with 5 fundamental forces instead of 4,
Whoa.
or where the speed of light is totally different.
Wow. Okay. My head's spinning a little bit.
I know, it's a lot. But those aren't even the wildest levels. Tegmark's Level 3 multiverse is based on the many worlds interpretation of quantum mechanics. So the idea is that every quantum measurement or even every choice that you make creates a split in the universe, leading to, an infinite number of parallel universes constantly branching off from each other.
So every time I have to decide between coffee and tea in the morning.
A new universe is born. One for coffee, one for tea.
I know.
It's a lot to take in.
It is.
And then finally, we have Tegmark's Level 4 multiverse.
Okay.
This one proposes that the universe is fundamentally mathematical.
Mathematical, yeah.
Yeah. Every consistent mathematical structure, every equation could correspond to a real physical universe. So math would be reality in a sense.
Okay, that one is really deep.
Mm-hmm.
But how do we even know if any of this is actually true? Can we even test any of this?
That's the big question. The multiverse, for now, is still very much in the realm of speculation. There's no direct experimental evidence to confirm or refute its existence.
So it's more of a playground for theoretical physicists right now.
For sure, but that doesn't mean it's not worth thinking about. And
Yeah.
even if we can't directly observe these other universes, there might be indirect ways to detect them. At least that's what some physicists believe.
Like what?
Well, some think that collisions between our universe and other universes might leave these subtle imprints on the cosmic microwave background radiation.
Okay.
So we're talking about faint patterns or strange temperature variations. Others think that gravitational waves, those ripples in space-time, could carry information about other universes.
So we're looking for clues, basically.
Exactly. The search is still on. And who knows, maybe one day we'll find that our universe isn't alone after all. Until then, I guess we can just marvel at the possibility.
Okay, so we've been talking about these grand cosmic ideas, but let's zoom in a little closer to home, relatively speaking.
Okay.
We've been discussing the origins and evolution of the universe as a whole, but what about the possibility of other worlds out there? Planets that might be home to life.
Right. And I know you sent in some material about the search for Goldilocks planets.
Yes. The idea of finding another planet that's just right for life is incredibly intriguing. I'm curious about, what makes a planet habitable in the first place, and what are the chances of actually finding life out there? Well, for a planet to be considered habitable, at least for life as we know it, there are a few key ingredients. First, it needs to be in the habitable zone of its star. That's the sweet spot, where temperatures are just right for liquid water to exist on the surface.
Right. Not too hot, not too cold, just right for liquid water, which we think is essential for life.
Exactly. But there's more to it than just the right temperature.
Mm.
A planet's size and mass are crucial too.
Okay.
If a planet is too small, its gravity might not be strong enough to hold on to an atmosphere. But if it's too big, it might become a gas giant, like Jupiter. And those aren't exactly suitable for life, at least not the kind of life we're familiar with.
So size matters.
It really does. And then there's the planet's composition, what it's made of. The presence of certain elements and compounds is really important. You need the right building blocks, things like carbon, hydrogen, oxygen, nitrogen. And of course, you need water, either on the surface or maybe in subsurface oceans.
So it sounds like there are a lot of factors that go into making a planet habitable. But with billions of planets out there in our galaxy alone, I have to imagine that there are at least a few that fit the bill, right?
That's the exciting part. Thanks to missions like the Kepler Space Telescope, which has already discovered thousands of exoplanets.
Planets orbiting other stars?
Exactly. We now know that planets are incredibly common in the universe. And out of all those billions of planets, statistically speaking, there are bound to be quite a few that check all the boxes for habitability.
So the search for life beyond Earth isn't just a pipe dream. It's a real scientific endeavor, and one that's turning up incredible results. It's amazing to think that we could be on the verge of discovering life on another planet, maybe even intelligent life.
It's definitely a mind-blowing prospect.
Yeah.
And if we ever did make contact with an alien civilization, the implications would be profound.
It would change everything.
Right, it would completely change our understanding of our place in the universe, our sense of loneliness, even our philosophical and religious beliefs.
It would be a paradigm shift for humanity. We'd have to face the fact that we're not alone in the universe. But even if we don't find intelligent life, just discovering any kind of life out there, even microbes, that would be huge.
I agree. It would show that life isn't some fluke of nature that's limited to Earth. It would suggest that life might be a common occurrence throughout the universe.
Life could be everywhere.
Exactly.
Okay, let's shift gears back to the subatomic world for a moment. We've talked about neutrinos before, those tiny, ghostly particles that barely interact with matter.
Right.
But you sent me some notes about a particular type of neutrino that's especially intriguing. Sterile neutrinos. What makes them different, and how do they connect to the mystery of dark matter?
So sterile neutrinos are a bit like neutrinos on stealth mode.
Stealth mode.
Yeah. They wouldn't interact with the weak force, which is one of the four fundamental forces of nature.
Okay, remind me what the weak force does again?
It's responsible for certain types of radioactive decay. And it also plays a role in how neutrinos interact with other particles.
Right. So if sterile neutrinos don't interact with the weak force, they'd be even harder to detect than regular neutrinos.
Way harder. They'd be like cosmic ghosts, passing through everything without leaving a trace.
And how does this tie into dark matter?
Well, because they're so weakly interacting, sterile neutrinos wouldn't emit or absorb light. They would essentially be invisible to our telescopes.
Okay.
But they would still have mass, and mass means gravity.
So they'd be invisible, but they still exert a gravitational pull.
Exactly. And that's why sterile neutrinos are one of the top candidates for dark matter.
They could be the missing mass, the invisible stuff holding galaxies together.
Exactly. If we could prove that sterile neutrinos exist, it would be a huge breakthrough in our understanding of the universe.
But if they're that hard to detect, how do we even begin to look for them?
It's not easy. One approach is to look for subtle anomalies in the behavior of other particles.
Like what?
Well, there was this experiment at Fermilab called Mini-Boon.
Right, I remember reading about that in those notes you sent.
So Mini-Boon was designed to study neutrino oscillations, the way that neutrinos can change from one type to another as they travel through space.
Okay.
And they found more electron neutrinos than they expected, which could potentially be explained by the presence of sterile neutrinos mixing in with the other types of neutrinos.
So it's like we're trying to catch a glimpse of these sterile neutrinos by looking at how they affect other particles.
Exactly. It's like a cosmic game of hide and seek.
It's incredible to think about how scientists can take these tiny clues and piece them together to try and unlock the secrets of the universe.
It's mind-boggling.
Yeah.
And the quest to find sterile neutrinos is just one example of the amazing work being done in physics today.
It makes you wonder what other breakthroughs are just around the corner.
Exactly. We're living in a golden age of discovery, and the future of physics is incredibly exciting. Now, switching gears just a bit.
Okay.
We've been talking a lot about real scientific concepts and theories, but I think it's time we address something that's more speculative, maybe even a little bit philosophical. I'm talking about the simulation hypothesis,
The simulation hypothesis.
the idea that we might be living in a computer simulation.
Right. It sounds like science fiction, but I know some serious people are taking it seriously.
They are. And there are a few reasons why it's gained traction, even among some scientists and technologists. One reason is just how complex and fine-tuned the universe appears to be.
Okay.
The laws of physics seem to be perfectly calibrated for life to emerge, which some people argue is a sign that our reality might be a carefully designed simulation.
So it's like if you find a watch on the beach, you don't assume it just randomly assembled itself. You assume there must be a watchmaker.
Exactly. And in the case of the universe, maybe the watchmaker is some super advanced civilization
Yeah.
with the computing power to create a simulated reality.
That's a pretty wild thought. But if we are living in a simulation, how could we ever know for sure? What kind of evidence should we be looking for?
That's the tricky part. Some people have suggested that we might be able to detect subtle glitches in the simulation.
Glitches.
Yeah, like inconsistencies in the laws of physics or unexpected patterns in the way matter and energy are distributed. It's like looking for cracks in the matrix, so to speak.
I love that analogy. But what if the simulation is so good that there aren't any glitches, or at least none that we can detect with our current technology?
That's a possibility. Some argue that if the simulation is sufficiently advanced, our simulated reality would be indistinguishable from a real reality.
So we might never know the truth.
We might not. It could be a question that's ultimately unanswerable.
Wow, that's both fascinating and a little unsettling.
I agree. But even if we can't definitively prove or disprove the simulation hypothesis, it raises some really interesting questions about the nature of reality, consciousness, and the limits of what we can perceive.
I think my brain needs a break after all that. We've covered so much ground today.
We have, from multiverses to sterile neutrinos to simulated realities. It's been quite a journey.
It has. What's the one thing you'd want our listeners to take away from this deep dive?
I think the most important takeaway is that science is all about exploration and discovery. We're constantly learning new things about the universe, and sometimes those discoveries completely change how we see the world.
It's like we're on this never-ending quest to figure out where we fit in the cosmos.
Exactly. And who knows what amazing things we'll discover next.
It's amazing to think about how much our understanding of the universe has changed. I mean, we went from thinking Earth was the center of everything to this picture of this huge, ever-expanding cosmos,
With billions of galaxies out there.
each with billions of stars.
And who knows how many planets.
It really makes you feel small, doesn't it?
It does, but in a good way. I
Yeah.
think it's humbling, but it also fills you with this sense of awe, you know? Like when you stand on the shore and look out at the ocean, it's vast and mysterious.
Yeah, I get that.
And I think that's what drives us to explore, to ask these big questions about the universe and where we fit in. It's that sense of wonder.
Speaking of pushing boundaries, we've covered some seriously wild theories today.
Yeah.
Multiverses, simulated realities, white holes, the idea that space itself might be a fluid.
It's mind-boggling stuff.
It is. But it's important to remember that even the craziest sounding theories, they come from real science.
Oh, absolutely. They're based on observations, data, math. They're our best attempts to make sense of the universe, even if we don't have all the answers yet,
And even if some of these theories turn out to be wrong,
or need some tweaking.
right, just the process of exploring them, questioning what we think we know, that's what pushes science forward.
Totally. You have to keep asking questions, challenging the status quo to make progress.
Okay, let's bring things back down to Earth for a minute. We've been talking about all this huge cosmic stuff, but what does it all mean for us here and now on this little planet?
That's a great question. I think one of the biggest things these theories teach us is perspective. When you think about the vastness of the universe, our everyday worries can seem a little smaller, you know?
Like, don't sweat the small stuff, but on a cosmic scale.
Exactly. It's not that our problems aren't real, but seeing them in the context of this massive universe can help us to reframe things, focus on what really matters.
It also reminds us that we're part of something bigger than ourselves, connected to the cosmos in ways we're only beginning to understand.
We are. We're literally made of stardust.
Stardust.
Yeah. The atoms in our bodies were forged in the hearts of stars. The molecules in our DNA, they were probably scattered across the universe by supernova explosions. We are, quite literally, children of the cosmos.
That's a beautiful thought.
It is. It makes you feel kind of insignificant, but also incredibly special, you know?
I get that. It's like this paradox.
Right. But it's a reminder that even though we're tiny in the grand scheme of things, we're capable of amazing things.
We've sent probes to other planets, built telescopes that can see billions of years into the past.
And we're always learning, pushing the boundaries of what we know.
Who knows what the future holds? Maybe we'll travel to other stars, figure out the mysteries of dark matter and dark energy. Maybe we'll even find proof of those other universes or simulated realities.
The possibilities are endless. It's an exciting time to be alive.
So, as we wrap up this deep dive, what's the one message you want to leave our listeners with? What's the most important thing to keep in mind as we continue to explore the universe?
I think the most important thing is to never lose your sense of wonder. The universe is full of mysteries, and the journey of discovery never truly ends. So keep looking up at the stars, keep asking those big questions, and never stop exploring.
Beautifully said. And on that note of cosmic inspiration, I think it's time to wrap up this incredible deep dive. It's been a wild ride.
It has.
From the tiniest particles to the grandest theories, it's clear that we've got a lot more to learn about the universe and our place in it.
We definitely do. But that's the beauty of it. The universe is this vast, mysterious place, and the journey of discovery is never-ending.
And who knows, maybe one day, one of you listening will be the one to make the next big breakthrough, solve the next cosmic mystery.
Until then, keep looking up at the stars and never stop asking those big questions. It all starts with curiosity, a thirst for knowledge. That's what drives us forward.
Thanks for joining us on this incredible journey through the cosmos. We'll see you next time on The Deep Dive.